And to understand the sheer engineering audacity of the Raptor 3, one must first strip away the spectacle of fire and the roar of the launch pad. At its core, a rocket engine is not a heat machine or a chemical furnace, though it incorporates both. It is, fundamentally, a momentum machine. To appreciate how SpaceX's latest marvel pushes the boundaries of what is physically possible, we must first revisit the foundational principles laid down by Sir Isaac Newton in the 17th century. While these laws are taught in introductory physics, their application in the vacuum of space and the high-pressure environment of a staged combustion engine reveals a complexity that defines the limits of modern aerospace engineering. In the great atmospheric misconception, there is a persistent myth, one that lingers even in the minds of some technically literate enthusiasts, the idea that a rocket moves by pushing against the atmosphere. In this mental model, the high-speed exhaust gases act like a foot kicking off the ground or a swimmer pushing off a pool wall. Under this logic, a rocket would be helpless in the void of space, with nothing to shove against. And this intuition is not only wrong, it is diametrically opposed to the reality of fluid dynamics and orbital mechanics. In truth, the atmosphere is an obstacle, a source of drag and back pressure that actively hinders a rocket's performance. A rocket engine is at its most efficient when there is absolutely nothing behind it. To understand why, we must step away from the launch pad and into a thought experiment involving a more relatable scale of motion. In the skateboard and the bowling ball, a study in reciprocity. Imagine a researcher standing on a high-precision, frictionless skateboard, perhaps one equipped with ceramic bearings to minimize any resistance. The researcher is holding a heavy bowling ball. Total system momentum is currently 0. There is no external force acting on the researcher, and they are not touching any walls or utilizing any external leverage. And when the researcher heaves the bowling ball forward with all their might, something inevitable happens. The researcher rolls backward. This isn't because the bowling ball pushed the air in front of it. It is because the act of accelerating the ball's mass required the application of force. According to Newton's third law, for every action, there is an equal and opposite reaction. The force the researcher exerted on the ball was mirrored by an identical force the ball exerted on the researcher. And in this scenario, the propellant is the bowling ball. The engine is the researcher's muscular system. The thrust is the resulting backward motion. The crucial takeaway is that the movement is entirely internal to the system of the researcher and the ball. The air in the room is irrelevant. In fact, if the room were a vacuum, the researcher would actually move backward slightly faster because they wouldn't have to overcome air resistance as they rolled. And this is the Newton connection. A rocket engine is essentially a device designed to throw bowling balls, or gas molecules, out the back at the highest possible velocity. The more mass you throw, and the faster you throw it, the more recoil you generate for the vehicle. And conservation of momentum, the balancing of the scales. To elevate this from a simple observation to an engineering principle, we must look at the conservation of momentum. Momentum is the product of mass and velocity, P equals m times v. In a closed system, the total momentum remains constant unless acted upon by an external force. And when the Raptor 3 ignites, it is essentially splitting a single system, the rocket, into two parts, the vehicle and the exhaust. If the exhaust gains a massive amount of momentum in one direction, downward, the vehicle must gain an equal amount of momentum in the opposite direction, upward, to keep the scales of the universe balanced. And this leads us to the fundamental challenge of rocket design. To achieve the high velocities required for orbit, roughly 7.8 kilometers per second for low Earth orbit, you have two primary levers to pull. You can either throw a massive amount of weight out the back, or you can throw a smaller amount of weight at an incredible speed. And in rocketry, mass is the enemy. Every kilogram of propellant you carry requires more propellant to lift it, leading to the tyranny of the rocket equation. Therefore, the most efficient engines are those that can accelerate their exhaust to the highest possible velocities. This is where the Raptor 3 begins to distance itself from its predecessors. By focusing on extreme exhaust velocities, SpaceX can squeeze more push out of every gram of methane and oxygen. And the molecular machine, how pressure becomes speed. If we zoom in from the macroscopic level of skateboards to the microscopic level of the Raptor 3 combustion chamber, the Newtonian push becomes a story of molecular ballistics. Inside the engine, the combustion of subcooled liquid methane and liquid oxygen releases an immense amount of thermal energy. This energy manifests as the frantic, high-speed motion of gas molecules, primarily water vapor and carbon dioxide. And these molecules are bouncing off the walls of the combustion chamber in every direction. If the chamber were a sealed box, the pressures would equalize on all sides, and the box would stay still. However, a rocket engine is a box with a hole at the bottom, the nozzle. And the molecules hitting the top of the chamber, the injector plate, exert an upward force. The molecules that would have hit the bottom instead fly out through the nozzle. Because there is no downward force to counteract the upward force on the injector plate, the engine moves upward. Thrust is literally the sum of trillions of molecular impacts against the internal surfaces of the engine. And the Raptor 3 specialty lies in the intensity of this internal environment. By operating at chamber pressures exceeding 350 bar, over 5,000 pounds per square inch, it packs more molecules into the chamber and hits them with more energy than almost any engine in history. Higher pressure means more frequent and more violent collisions against the top of the chamber, which translates directly to higher thrust. Furthermore, this high pressure allows the nozzle to expand the gas more effectively, converting that chaotic thermal energy into directed kinetic energy, meaning the bowling balls are being thrown out the back at supersonic speeds. And the relationship between mass flow and velocity. To understand the design trade-offs of the Raptor 3, one must appreciate the relationship between the mass flow rate, how much propellant is burned per second, and the exhaust velocity, how fast it leaves the engine. And thrust is calculated as the product of these two variables. You can get 200 tons of thrust by throwing a lot of mass slowly, or a little mass very quickly. However, the efficiency of the engine, what engineers call specific impulse, ISP, is determined almost entirely by the exhaust velocity. And think of ISP as the miles per gallon of the rocket world. An engine with a high exhaust velocity is stretching its propellant, getting more momentum per kilogram. This is why the Raptor 3 uses a full-flow staged combustion cycle. By pre-burning the propellants in pre-burners to power the pumps, and then feeding that high-energy gas into the main chamber, the Raptor ensures that every molecule of propellant is fully energized before it is expelled. It maximizes the velocity component of the momentum equation, allowing Starship to carry heavier payloads with less fuel. In the vacuum paradox and nozzle expansion, returning to our debunking of the pushing against air myth, it is vital to discuss why the absence of air is actually a benefit. In the Earth's atmosphere, the surrounding air pressure pushes back against the exhaust as it tries to exit the nozzle. This back pressure effectively bottlenecks the engine, preventing the exhaust from expanding as much as it would like. And as a rocket climbs and the atmosphere thins, this back pressure disappears. The exhaust gas can expand more freely, accelerating to even higher velocities. This is why rocket engines have a lower thrust and efficiency at sea level than they do in a vacuum. And the Raptor 3 is designed to navigate this transition. Its nozzle is a precision-engineered bell that guides the expanding gas. If the nozzle is too small, the gas doesn't have enough room to expand and reach its maximum velocity. If the nozzle is too large for the atmospheric pressure, the outside air can actually crush the exhaust flow, leading to flow separation and potentially catastrophic vibrations or engine flutter. And the Raptor number 3 achieves a high area ratio, the difference between the tiny throat of the engine and the wide exit of the bell, while maintaining such high internal pressures that the exhaust remains stable even at sea level. It is a brute force Newtonian machine that uses sophisticated thermodynamics to ensure the reaction is as violent and directed as possible. And momentum as the foundation for Starship. Everything about the Raptor number 3, from its 3D printed internal cooling paths to its simplified, manifold-free exterior, is a servant to Newton's second and third laws. The engine is a conduit for momentum. By burning methane and oxygen at pressures that would liquefy most other materials, SpaceX is creating a mass driver of unparalleled power. And when we see Starship rise from the pad, we are seeing the culmination of this momentum exchange. The millions of pounds of thrust are the aggregate result of billions of chemical bonds breaking and releasing their energy to fling mass downward. The vehicle does not care about the air. It only cares about the velocity of its own discarded weight. And the Raptor number 3 is the ultimate expression of this principle because it pushes the variables of the momentum equation to their logical extremes. It seeks the highest possible mass flow rate through the smallest possible throat at the highest possible pressure. This creates a density of power that allows a vehicle as massive as Starship to not only leave the ground, but to do so with enough leftover energy to carry the hardware necessary for total reusability. And as we move from the abstract physics of momentum and the why of rocket thrust, we must look at the how. To generate these forces, the engine cannot simply be a hollow tube. It must be a complex symphony of plumbing, spinning turbines, and precision machine chambers. Understanding the Newtonian requirements of high-velocity exhaust sets the stage for the mechanical complexity required to handle such forces. To throw the bowling ball at several kilometers per second, you need a very sophisticated set of arms. And in the next section, we will transition from the laws of motion to the physical hardware that makes these laws work in the harshest environment known to man. We will examine the skeletal and circulatory systems of the engine, the components that house the fire and direct the flow. In 1.2, the anatomy of a rocket, tanks, pumps, and bells.